to my screen. Let's see. All right, can you wait? Let me see. Yeah, you should be able to see my screen. Okay, so yeah, this week we're gonna go over logistic regression, which just to start off, it's kind of a misnomer because it's actually a method for classification, even though it has regression in the name. But yeah, and unfortunately this week's lesson might be kind of short, and there's not going to be a code sample today because Kaushik is not able to make it today. Because yeah, the college apps are coming up. November 1st deadline. Next week might be the same as well. Hopefully not, but the week after that should definitely I guess return to quality. But yeah, so it's just me for today. Um, yeah, with that, let's just get started. Yes, we're gonna go over these things like why do logistic regression, the logit function, the coefficients of logistic regression, the maximum likelihood loss function, and R-squared. All right, so first off, why would you do logistic regression? Well, the first thing to understand is that logistic regression, like I said at the very beginning, is actually a method of classification. And the um, the primary use case for logistic regression is actually binomial classification, where you only have two possible classes, right? It's like yes or no, true or false, red or blue, whatever, right? Any feature that has two possible classes. And so, that's the classification output, right? Where you have a discrete output of one or zero or, true or false. Um, but you also have the thing with logistic regression is that it also takes numerical or continuous inputs, right? Which is interesting. And so when you see a graph like this, right? If you just ignore this like logistic regression line, you can see it gives you information about whether or not somebody passed the test and how many hours they studied, right? So this would be a data set with with one feature and one label, right? Where the feature is a numerical continuous value of how many hours they studied, like 0.5, 2.1, whatever. And then the output would be whether they passed or not. So true, false, yes, no, yes, yes, blah, blah, blah. Right, and here they have it mapped from 0 to 1. Right, and the reason you're allowed to do this is because the output of logistic regression is actually similar to naive Bayes. It's a probability that it outputs, but rather than yeah, it's basically a probability that it outputs. And as you probably know, um, the scale of a probability, right, is 0 to 1, 0% to 100%. And so, that's like saying, a probability of 0 is saying, oh, there's a 0% chance they pass the test. A probability of 0.9 is like 90% chance they pass the test, right? So like, 9 out of 10 times, right? And, that's all well and good. But the problem with this is that linear regression is not bounded to 0, not bounded by anything actually, not from 0 to 1, right? So that means if, I was to draw like, this is our features, right, or our data set, right? And you're just to draw like a simple line of best fit through them, something like this. The issue with that is that at this point, right, say B, after this point, the probability that it outputs would be greater than 1, right? And similarly, at this point A, anything below A would give out a probability less than 0 for when you try to predict with the simple linear regression model. And so obviously that doesn't make any sense, right? You can't have any negative probability or probability greater than 100%. And so that's where logistic regression comes in. Whereas you can see by this curve, it's bounded from 0 to 1 and it gives a probability. And also the domain of logistic regression curve is all the real numbers, right? Negative infinity to infinity, right? So like you see here, range of linear regression is, any number, right? Which can be greater than 1 or less than 0. And the probability can only be between 0 and 1 inclusive, right? And so now I'm going to need to teach you a few simple statistics concepts that are important here. And so an important thing to know here is say, let's create a simple data set, right? Let's say that you're measuring like mice, right? And you're trying to predict whether or not they're considered, or they're classified as obese. Okay, so obese, and then the input is like their weight, right? So you're given their weight in grams. So it'd be like, whoops, that's bad 5. 50, 61, 62.1, 71, 60, right? And then obesity is like no, no, yes, no, yes, right? And so, like I said earlier, this is a continuous numerical input with a binomial class output, right? And so the one thing to take note here is, first of all, what's the overall probability that a mouse is obese, right? Without taking weight into consideration. Whoops, wrong tool. If you only look at the right side, right, the single column of obesity, if you were to pick a mouse at random from your data set, what is the probability that it's obese, right? Well, this is simple, right? You just count up the yeses, so it'd be 2, and then divided by your total number of observations, right? So 1, 2, 3, 4, 5, 2 over 5, right? 0.4. And that's all well and good, right? You have 40% probability of getting a mouse that's obese if you were to pick one at random. However, there's also another measure of that's related to probability called odds, right? And you can think about odds like this, right? So if you were to you have the 2 yeses, right? So you have 2 yeses, and in relation to the no's, you have 3 no's. So 2 to 3 odds, right? And you're saying, for every 2 yeses, there's going to be 3 no's, right? 3 that are not obese. And so, as another example, like say that, given like your basketball team, right? And you're trying to predict how much you're going to win. And in the end, your odds are 1 to 10, right? So against a particular basketball team, your team has a 1 to 10 chance of winning, right? Where the other team has 10. And this is just the odds, right? This is the chance that your team wins, and this is the chance that the other team wins, right? And if you're like probability, right? You have the chance of you winning divided by the total observations. So 1 divided by 11, right? And you can see how they're related, right? You have 1 to 10. So if, actually, yeah, I think I made it clear enough. It's basically the probability of it occurring to not occurring, right? So this, the odds of this, right, the total odds for a mouse being obese would just be 2 over 3, right? And the thing with this is if you have a binomial distribution, you actually don't, you can actually get it from the probability, right? And so the reason you can do that is because, well, first of all, let's look at the probability, right? It's 2 over 5. 2 over 5, right? And so that's a chance that your team wins, right? And if you have a given, if you have a probability here within a binomial distribution, right, 2 out of 5, that means that you know what the other probability is, right? The probability that the mouse is not obese, because it's simply 1 minus your probability, right? And this gives 3 over 5, and 3 over 5 is the probability that your mouse is not obese, right? And this is exactly what we want, right? We want the probability that it is obese divided by the probability that it's not obese, right? And again, if you were to just get the simple probability, right, this would be probability of it being obese versus every single possibility. But that's not what we're doing here. Here we're taking the odds. And so again, 1 minus 2/5, we get 3/5. And once you simplify, you end up with 2/3 again. Right? So that's odds, right? Not too bad. And so, but the interesting thing about odds, right, is that it changes it changes the range of this transformation is different from the domain. And so what I mean by that is if I'm to like open up Desmos here, right? Remember that we calculated this, right? Let me write back the formula here. This is how we calculated the odds of the mouse being obese, right? So let's just replace these numerical inputs with variables, right? So P of X, 1 minus P of X, right? This is, whatever probability you're trying to predict, this is getting the odds of that probability given a binomial distribution, right? This is the formula. And so remember P of X, right? The probability of, anything here, but for our case, mouse being obese, it ranges from 0 to 1, right? It's a value only between 0 and 1. And so for to graph this, right, X over 1 minus, 1 minus X. Well, actually, let me, we're only considering the cases between 0 and 1. Here we go, yeah. So this is what we get, right? So, X going from 0 to 1, right? That would be our input. But we can see that our output range is actually 0 to infinity, right? And that's actually a particularly useful transformation that we can make that I'm going to explain later, right? And so, that's what we see here, right? That's what this bullet point is showing, right? That it transforms our, it has a domain of 0 to 1, including 0, and the range of it is 0 to infinity, right? And remember, this is a function of a probability. And the next thing that we need to do is now we need to transform it from negative infinity to infinity. And why do we do this? Well, that's the range of our linear of a linear function, right? And so what we can do here to make it range instead of from 0 to infinity, instead to negative infinity to infinity, is take a log of the whole thing, right? And so we take this formula for the getting the odds of an event given the probability, and we just get the log. Oh, well, this is the natural log, but I'm just going to keep referring it to the log. Just in case you don't know, natural log is, log base E, right, where E is Euler's number. Right, so we have this natural log. And, well, why is this possible? Well, if you look at the function ln of x, right, our output for the, original odds function, just this part inside, right, is from 0 to infinity. But if you notice, that's also the input of our ln x, right? X can only be greater than 0 and, greater than 0 all the way to infinity. And the range of log of x is also negative infinity to infinity, right? So if we apply this this function, then we get this. Oh, it's kind of hard to see here, so I'll do like a log base 10. Or, yeah, something like that, so you can see it better. So this is what it ends up looking like, right? And this is, the important function to know, the logit function, right? And remember, the logit function is the log odds of the probability, right? And this completes the transformation that we need, right? From a scale of 0 to 1, we can use the odds to get it from 0 to infinity. And then from there on, we can use the logarithm function to get it from 0 to infinity to all the real numbers, right? Negative infinity to infinity, right? And so, again, why is this important? Why do we want to do this? Well, changing the scale of our output to all the real numbers makes it so that we can use a linear based model, right? And this is something important to note. So logistic regression is actually very similar to linear regression, and they're actually both sort of under an umbrella term or an umbrella like method, or I guess collection of methods called the general linear model, right? And the general linear model essentially follows the form of some function of x is equal to some intercept plus beta terms for every single input feature you have, right? So if you had two input features, right, be beta 1 and beta 2, one for each input feature, and then beta naught for the intercept. And so this is like the very generalized form of the linear regression model, because here you can see that the linear regression model is literally just y, right? And you plug in y for there, and then you have this model, right? But what we want to do here is instead of y, we want to fit it to the logic function we had earlier, right? And so, like I said before, we're able to do this because we made the transformation of our input probability into a scale of negative infinity to infinity. So instead of just y here, like we would for normal linear regression, we can plug this in, right? We can have ln of y over 1 minus y, where y is our probability, right? And so what does this mean we can do? Well, if you look at this graph here on the very right side, this isn't actually a normal like graph comparing x to y, right? So this is a logistic regression, and we're actually looking at a graph scaled by logit rather than just by one, right? So this is comparing. So in this graph where you only have one variable to compare, so just take out this beta term, right? We're comparing this line of beta naught plus beta 1 x1, where x just scales linearly, right? 1, 2, 3, 4, 5, 6, right? And instead of graphing it against y, we're graphing it against this function, the logit, right? And so that's what we see here. And what's important to note here is that these dots at the top and bottom are actually the our input data set that we're training on. And so, why is it all the way up here and down here? Well, let's plug it in to our function and actually see what it ends up being. So for our data set here, right, we can consider no to be equal to 0 and yes to be equal to 1. Right, that's how you generally apply it to like a number line. Right, so let's consider the no's, zeros, and the yeses, ones. So our graph would look like 50, 61, 62.1. So it would look something like this. Let me make this a little bigger. It looks something like this, where this line right here is equal to 1, right? And so if we want to go from, remember, this is the normal number line, right? This is going up linearly. Right? If we want to transform from the normal number line to our logit scale, we're gonna have to apply the transformation, right? The formula that we have for the log odds, right? So for 1 as our y, right, we're gonna have let's look at this top right one, right? That would be where is it? I guess 62.1 yes, right? So for a y, we have ln of y would be 1 over 1 minus 1, right, equals whatever line, right? You'd apply this transformation, and this would be the location of your y on your new logit scale, right? But as you can clearly see here, this gives us an error. We can't divide, we just get 0. But one thing we can do here is by the properties of logarithms, you can actually do log of 1 minus log of 0. And we know that log of 0 approaches negative infinity, right? So we can say that the y value of our of this particular point approaches negative infinity, right? And you can see how that would be true for every single other y value with 1, right? You'd yeah, you can see why. And so we can also do the same thing for let's see, for 0, where, let me see, again we can get what is it, like this one, for example, right? So ln of 0 over, oh yeah, I apologize. Yeah. Since I put negative infinity, right, minus ln of 0, right, this approaches negative infinity, so it would approach negative infinity or positive infinity. Yeah, that's where I was getting mixed up. Yeah, that was my mistake. But yeah, so these ones should approach positive infinity, right? And so when we look at these zeros, we get 0 over 1 minus 0, right? And again, we can see that ln of 0 minus ln of 1, right? Ln of 1 is just 0, and ln of 0 approaches negative infinity. And so negative infinity. And so you can see these bottom values within our Logit scale actually approach negative infinity. And these positive values within our Logit scale approach positive infinity. Right? And that's why they look like this in the graph. Right? You have them at the very top and bottom. Right? But that poses another issue for us, because we have this Logit scale, right? And we have this normal like linear model that we can apply to it, which means we should be able to do like least squares or something. However, the problem is that we can't get a residual here, because the residual is just the distance between the two squared, right? And then you add them all up. But here, instead of having like definite values, you just have values that approach infinity or negative infinity. And you can't use that for least squares, right? Like there's no way to optimize infinity. And so what are you going to do here, right? Or yeah, what is there to do here if you can't use the same methods that we could before? Well, being able to solve this issue, right, in this way, because of this problem here, requires us to use numerical estimation techniques instead of just an algebraic nice formula we can use, right? Because with linear regression, you could literally just plug in, f of, all our data points, right? And that would give us, beta naught and beta 1 values, right? That we could just use, after we finish calculating them as our line of best fit. But here we can't do that, right? So here we're going to have to use basically linear approximation techniques. And so what this might look like is say like the actual, like for beta naught, right? Say for this parameter, the actual best, like most optimized value would be like 5, right? And so what this would look like, right? Instead of just solving and getting 5 immediately, you'd start out at a random number, so like negative 10 or something, right? And then essentially you just go around trying different parameters in an intelligent manner to be able to try and get close to your target value, right? So you might get negative 10, and then in your next iteration, you might get negative 1, then you might get 3.2. Right, your next iteration, you might get 4, then you might get 4.6, right, 4.8, right? Always approaching and estimating, your best value, right? But like I said, we don't have any like analytical, like algebraic method to do this. This is all we have, right? Because, like I said, because of the issue before with the infinite residuals, right? And so, or what are our actual parameters here, right? I've been describing our beta naught and beta 1s, right? And so, we know what they are in terms of the Logit scale, right? The Logit space where, it's just a line, right? They just describe, the relation between x and this function, right? The ln of y over 1 minus y. Right, but how do we actually solve for them? Well, it's actually not too bad. You know, for here, you just take the exponentiation of both sides. So e to the this and then e to this, right? And you'd end up getting y over 1 minus y equals e to the beta naught plus beta naught or beta 1 x1. Right, and then you multiply both sides by 1 minus y. And then, you know, you get left with this. Right, after multiplying by 1 minus y, then you just add, you know, y e to the beta naught plus beta 1 x1 to both sides. And you get this. Right, then you group these two terms together. You get y1 plus this thing equals this thing, 1 x1. And then you can just divide both sides by this. Right, and then you get your final term for y. And it's equal to this. So this is our final formula for the logistic regression function. All right, and so you know, let's actually see what it looks like. Let me pull up. Let me see. Yeah, I had this pulled up. So let's copy this function. Right, we had y equals e to the beta naught plus beta 1 x1. So e to the beta naught plus. Whoops. Okay, I kind of hate Desmos. There you go. Divided by 1 plus all that. And then let's, instead of x1, let's just put x. Right. And so here we have our, you know, this is for beta naught and beta 1 for both 0. We have this. So we can see as we play around with this function how it affects the final estimator, right? Because remember, we solved for y, right? So we solved for, you know, this is returning back to normal linear space, right? Where everything acts as we expect. And, you know, our original function, rather than taking on a linear form within the Logit scale, it looks like this within like a normal graph. So you can see, you know, beta naught seems to change the intercept. Beta 1, you know, it changes like how curvy it is in the middle, but this is a bit deceiving because it doesn't actually change as you might expect as you change both of them simultaneously. Right, now it does this like weird rotation thing. All right, but this is essentially what the logistic regression formula, what the algorithm creates, right? It creates a graph or a line of this form, given these two input parameters, and these, like we saw in linear regression, these are just model parameters that need to be optimized. And like I showed earlier, rather than using some nice algebraic formula or method, we have to use a numerical approximation. And so unfortunately, the method for actually approximating that is outside of the scope of this class or this course thing. I don't want to call it a course. That sounds like I guess a bit self-indulgent. But yeah, unfortunately, it uses concepts from vector calculus. I can teach you like the basics. So one of the ways is using something called the Newton-Raphson method, which looks like this, where x of I is equal to, x of I plus 1 is equal to x of I minus, f of x over f prime of x, right? Where f prime of x is the derivative, right? And this method is used to find the roots of a function, right? Wherever the function is valued at 0. And so if you have a function that looks like this, right? And you were to start here, right? Your x1 was to like right here, You'd apply this formula, you end up here. You apply it again, you end up like here. You do it one more time, you get like closer and closer. And so you eventually, you converge onto the 0, right? And what you may notice, the reason this can be used, no, this is just an example. Oh, f of x, I mean like if you're to apply, so like if you're to apply a function f of x, right? So in this case, f of x would be like a y. Oh yeah, sorry, I meant f of x I. Yeah. Yeah, I apologize for that. But yeah, you just apply it and it would converge onto a 0 of a number of your graph. Right? And so the reason you can use this is because there's actually a special loss function that we're going to use for this that I can't actually show you, which is called the maximum likelihood. This GIF might get a bit distracting, but essentially it works in the following way. Let me see. So what you do is, you have your predictions. Oops. All right, this is your data set. Right, and your line looks like this. Something like that. Right? And so what the maximum likelihood estimation is you start with a given point, and you take the probability of predicting that point's class. So for this point on the very right, say that the value of this function is like 0.99 at that point, right? And that's a probability that the function predicted, right? This blue line, that's a probability that of our model predicting that class correctly, right? That's a probability that it gave. And so, we have that class. We go into this one, right? It's again like 0.99. Next one is might be like 0.98. Next one would be like, I don't know, 0.92. You continue here. This one might be a little lower, like 0.84. This one could be like 0.48. This one would be like, I don't know, 0.21, right? And so that's all the estimations, right? All the probabilities given by the model for these top these data points. What about these bottom ones? Well, if you notice, if we go back to our example of like mice and obesity, these would be the data points of obese mice, and these would be the data points of mice not being obese. And again, if you remember, the probability of a mouse not being obese is 1 minus the probability of it being obese, right? P of x. And so here, since it's trying to predict the probability of the mouse not being obese, right? It gives a 0.9 rating per 0.9 probability that it is obese, which means that it gives a 0.1 probability, right? 1 minus 0.9, 0.1 probability that it's not obese. And so, we add that, or no, we don't add that. We multiply that, and we continue our multiplication here. So we get times 1 minus 0.9, right? Times 1 minus 0.48 or 49, right? Times 1 minus, I don't know, 0.16, right? And then again, we just continue doing that for the rest of these, right? And if you remember from the pi notation, in that notation, it would look like this, where in 1 of p xi times restart dot s n yi 0 of 1 minus p xi. right? And so what this is essentially saying is this, right, this for S and yi equals 1. This is just getting all the data points where, where yi equals 1, where the mouse is obese, right? And then it's getting just the probability, right? And by this pi notation, it's multiplying them all together. And then the same thing here, right, where S is, where yi is 0, right, where mouse is not obese. And then we're just getting 1 minus the probability that it is obese, right? And so this is, this is denoted L of B or beta, because this is actually dependent not just on the data points, but on the parameters, right? If you have a function, that looks like this, right, that would definitely get different results from our blue line here, right? And so this beta is a vector where represents all of our parameters. And so but yeah, so you can see how the probability is from 0 to 1, right here, and probability is also 0 to 1 here, right? Just 1 minus a value from 0 to 1 is also 0 to 1. And so here are the range of this function is 0 to 1, right? But in practice, like given a an actual logistic line, right, it would never actually reach 0 or 1. So we could just write it like this, right? But that's not too important. But the issue is that as you get a lot of data points, these lower values can get to be very, very close, and it gets very difficult to tell the difference between them, because if you have like thousands of data points, right, of getting a good model and a bad model, maybe the difference between like 0.002653 blah blah and like 0.002649 blah blah, right? And those are very small differences, especially at the lower levels. And so one thing that's done here is you also take the log of this entire equation, and it also makes it easier to deal with, because if you know the properties of logarithms, well, actually, I have to simplify this first before we can get to that. So one way to simplify this is to rewrite it as like this for S, and P of xi of yi times 1 minus p xi 1 minus yi. All right, and this is saying the same thing as above, even though it may look different. Because if yi is 1, right, remember, these are the top values where it should just be the probability, right? If yi is 1, this is going to be 1, so probability of xi to the power of 1 is just probability of xi. And then 1 minus 1 is 0. So this entire term is just going to turn to 1, right? It's going to be ignored, right? So in the case that yi is 1, you get left with this case. And in the case that yi is 0, then this term gets ignored, and this term, gets to the power of 1. And so that's the one that's considered. And so in the case that yi is 0, then you get left with this. And so that's why this is the same thing as the above. And so if you take the logarithm of it, you can actually split this up, right? And you can do all sorts of where log of like a to the b is equal to b log a or whatever, and all those fancy log tricks you can do help make this calculation a lot easier, right? And turn this multiplication into a sum. But we're not going to get into that whole thing. But essentially, this is the function that you're going to be optimizing, right? And so when you take the log of this, right, so let me move this down. Then we get the this whole thing. This is going to be the function you're going to be optimizing given your input parameters of your beta parameters, right? And so if you remember, we defined this and then we set the partial derivative with respect to each beta parameter to 0 to be able to find the minimum. And but we can't do that here, right? We have to find beta parameters that minimize this numerically, right? Just using estimations. And so now this is like similar to that Newton-Raphson method that I was talking about before, where it finds, if you're to have a model like this, it finds the closest root, right? And so this model, if it's between 0 and 1, right? This inside term is between 0 and 1, right? And you're applying a log to it. Well, if we put that into Desmos, right, you can remove these. Right, you can see that for values of x between 0 and 1, right, this maps the input from 0 to 1 to a range, right, or an output of -infinity to 0. Right, and again, with the Newton Raphson method, right, this is just going to find 0, right, the nearest the root, right, the 0 value. And so this is the actual like error function that gets optimized, right? Similar to the error function where with like ordinary least squares, where it's just like the differences squared all summed up, right? This is the same thing but for logistic regression. And so but yeah, that's essentially the like the optimization technique, right? The function you have to optimize in order to get a better prediction. And here you can see what it looks like, right? As it goes through iterations, right? It starts out with a very like generic, like not very optimized model here, and then as it gets as it makes more predictions, it gets closer and closer to the actual like best model it can create, right? You see it how it's modifying these beta naught and beta 1 parameters simultaneously to be able to achieve that, right? And so and so but yeah, that's the last thing. And one last thing we're gonna have to do differently between this and linear regression is Rsquared, because with linear regression, right, you're just getting the difference between between the raw values and their outputs, right? There's a numerical prediction, right, where you have dots, right, data points, and you just get the differences between the line and the data points, and you square them. Right, but for logistic regression, you're not actually predicting a numerical value. You're giving probabilities, right? So you can't just get the squared distance. And so for logistic regression in particular, there's no like standardized, like definite R-squared method. There's like over 10. I don't know how many there are in total, but there's a lot. And it has to it changes from field to field, right? Depending on what your application is, right? And what other scientists in your particular, like what you're working on are doing, you might have to use different R-squared methods. But the most popular one is definitely the McFadden's pseudo R-squared. And we can actually derive that from our original R-squared. And so if you remember from our linear regressions lesson, we had SST minus SSR over SST as our R-squared, right? Where our for our given data points that I'm just gonna draw here, right? The SST is the right where you have this mean line. The SST is just the sum of all the squares of the total distances from the values to the mean line, right? So you take all these differences and you square them. And then the SSR is the least squares, right? And so that would be like this, right? And you'd be getting all these differences and squaring them, right? And so that's how we calculated it for linear regression, but we can actually find the same analogs for these functions within logistic regression. So first of all, let's do SST, right? So for the sum of squared totals, so let's go back into rather than normal like linear space, let's go back into logit space or logit scale, I guess, where you have you have 1, 2, 3, infinity, right? And then now your that's where your prediction, or not your predictions, your data points would go, right? So like we saw in that other graph, they'd go here, right, and here, right? So this is what it would look like within logit scaling. And so what can we do to find the SST? Well, if you remember, like I said before, SST is a difference I deleted that drawing. But SST is essentially the difference between the mean line and the the mean line and the all the individual data points, right? You get all their differences, you square them, and you add them up. Right. So here, how do you find this mean line? Well, one way we can do that is to get the log odds, the logits of our data without taking the input into account, right? And so if you remember, if we had this data set, right? And what linear regression is, right? When you get the mean, right? Getting the mean of a data set, right? Just getting the average value is sort of like doing a, let me see. It's sort of like trying to predict the value without taking the your prediction variable, your independent variable into account, right? Since its slope is 0, the correlation, there's no correlation between this line and the input variable, right? So you're not taking it into account. You're only trying to predict it based on the output. And we can do the same thing for logistic regression, right? So if we go back to our data set, you can again take the log odds of our output without taking a weight into account. And like we calculated before, the log odds of it would simply be ln of 2 over 3. And so if you plug it into Desmos, negative 0.4, right? And so that's what our mean line would look like within our logit space, right? So if I draw this here, right, if this was 1, then it'd be somewhere like here, right? And so we have this mean line, but we still can't get any residuals from it here because again, the distance between everything is infinite, right? So we're gonna have to convert it back to normal scaling before we can get any residuals, right? And again, to get from normal, like y is linear, to logit space, we're gonna have to use that equation, right? It's equal to ln of what was it? It was y over 1 minus y. All right, so we're gonna have to well, let's denote this like YL for like Y logit space, right? This so now we're gonna have to, instead of going from our Y normal, right? So I'll just write YN. Instead of getting from our Y normal to our Y logit space, we're gonna have to go backwards, right? Convert this whole thing back into a normal graph. And so for that, we can simply solve for Y normal, right? So if we get E, my E's are so ugly. Okay, E to the YL is equal to Y normal over 1 minus Y normal. Multiply both sides, by 1 over Y normal. So you get something like this. Right. And then, just distribute out the E to the Y logit. So you get, oops. Oh my God, there you go. All right, we get something like this. And then, we just continue, we just add this to the other side. We undistribute it out, right? We group them together. So 1 plus y logit, e to the y logit. And then we just divide both sides by this inner term. And then get left with this, right? So this would be the term for going backwards, right? This would be the formula. So now, we have formula for going into the logit scaling and going back from logit scaling back into normal graphs, right? And so that's what we want to do here, right? We want to take this and turn it back to normal. So then we just plug it into our, this is our y, logit, right? So we just plug it into that formula. So then we can get e to the, I'll just denote that L here just to make it easy. Over 1 plus e to the L. Right, yeah, that was it. And then our original value was this, negative 0.4, blah, blah, blah. Right, and we get 0.4 as our output. And so what that tells us is within normal space, right, within this, within this representation, you get y equals 0.4 as our mean line, right, which should look like this, something like that, yeah. And so, so then from here on out, then we can continue, and then we can pretend this is our model, right? We can, like we did with the linear regression, right, where we got the difference squared, right? But this time our error function is not the difference or the sum of squares. Instead, it's the maximum likelihood, which is this thing, right? And since this is 0.4 for everything, right, this is just gonna look like when we actually put it into this formula, it's just gonna be like ln of 0.4 times 0.4, blah blah blah, right? And then once we get to these bottom terms, it's gonna be again 1 minus 0.4, so 0.6 and 0.6. Right? And so this is gonna be like our baseline, right? This is gonna be similar, serve the same purpose as the mean line did for our SST or for our linear regression. And so this is gonna replace our SST, right? So instead of SST, we're gonna write log likelihood. So let's see, log just LL, I guess, of our I don't know, the overall probability or something. So probability, right? So LL of our overall probability. And then now we need to do the same thing for SSR. So in the example of linear regression, what SSR did, it was the same function that we used for as our error function, right? That we try to optimize, where it's just the difference is squared. And so here, we actually have that same function here. This is our the one that we're trying to optimize. And so what we can do now is given our move this here. So given our input, right? So if we hit input like beta 0 is like, I don't know, 0.5 and beta 1 is like 0.9, right? Given those input parameters, we can predict what the log maximum likelihood is, right? And so we can put log likelihood of our model's fit, right? Beta. Right? And again, this beta is just a vector for, I can write like a hat over it to make it better to denote as a vector. That's the parameters of our model, right? And so this is how we can calculate R-squared, or actually not R-squared, the McFadden's pseudo R-squared, right? And like this slide says here, the R-squared here is much more likely to be less than the traditional R-squared from linear regression. And so here where you may have an R-squared of like 0.8, right? A logistic regression of equal like predictive strength might have an R-squared of like 0.31 or something. Right, and so this is how you are able to get that same R-squared metric for a logistic regression. And I think that's all for logistic regression. Yeah, that's pretty much it. So we went over the the log likelihood, which is the function we're optimizing. The coefficients of the function. Yeah, odds and logs odds. One more thing that I want to go over real quick. Now I'm probably gonna go over again later in the year. Is that, like I said before, the what's it called? What's the other method called? It was like the Newton-Raphson. That's what it was. Yeah, the Newton-Raphson method. That you're able to use to optimize for right, to find 0 points. Right. This method right here, it seems pretty simple for one dimension, but unfortunately, I can't show it for higher dimensions, right? Because for our case, right, even with a single variable, we have 2 parameters, right, 2 dimensions, beta naught and beta 1 that we need to optimize. And yeah, like I said before, this I can't show it here because as you increase dimensions, this turns into like a gradient vector. This turns into a Hessian matrix, and yeah, those are just concepts within vector calculus that are just too advanced. But another method that's actually a lot more popular and important for machine learning in general these days. That's not just for finding zeros of a function, right? Because this method is for finding zeros of a function, and for our if you remember, for our use case, right, the maximum or like our optimized version happens to have 0 as like the best possible optimization, so we can use it. But otherwise, there's this method called gradient descent, and it's actually very similar to the Newton-Raphson method, right, where this is the formula. So instead of having this formula, the gradient descent works like this. Right? Yeah, x of I plus 1 is equal to x of I plus alpha f prime. Yeah, f prime of xi. And the way this method works is instead of finding a 0, it finds any extrema. Well, actually, not just any extrema. It depends on what you have for your alpha value here, right? And again, I'll go over this more in detail later, but for now, I'll just give a quick overview of it, like I did with the Newton-Raphson method. So if you have a function like this, right, and you start out here, right, instead of just going and finding the 0 here, it's gonna keep going. It's gonna go to the next approximation, right? It's gonna find it here, here. It's just gonna find the local extrema, right? The lowest number, right? And that's if this alpha value is negative, right? If we have if we have a positive alpha value, on the other hand, this is also known as the learning rate. Then it's gonna look for local maxima instead. So if we started here and our alpha is positive, right? Then we go here, 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 and we eventually converge onto like this local maxima that we find. And so that's just another way to achieve the same thing with optimizing this function, or not just the ln function, but this whole thing, right? So it's just another way to achieve it, and this is also used a lot more in just as a general numerical approximation method, and optimization method. Especially in stuff like neural networks that we're going to be learning about later. But yeah, that's pretty much it for today. I apologize if the lesson was like of lower quality, or if you weren't able to learn as much. But like I said, in 2 weeks from now, we should be all good. But yeah, is there any questions? There usually aren't, anyways. Let's see. But yeah, I think we're good. So we can just end the meeting here. Let's see. How do I stop recording?